Hello, today we're going to talk about structure 2.2.11 and 2.2.12. This one is higher level only, and it has to do with resonance structures, and we're going to focus in on benzene as part of that. Okay, so resonance has to do with pi electrons. So let's say you have a compound and you have multiple atoms around a central atom. This is a decent starting point for us to talk about this. The single bonds are considered the sigma bonds, and when you add an additional, like a double or a triple bond, those are considered pi bonds. And those electrons that make up the additional bond, if there's more than one spot for that double bond to go, those electrons are what we call delocalized. Delocalized. So effectively, I should draw in the lone pairs on the oxygen atoms like this. Each of the single bonds is 2 electrons in there. And those are localized. They have to stay in between the carbon and oxygen in that orientation to maintain that there is a bond there. The other oxygen atom here definitely has to have 2 electrons be localized to keep it bonded. But then there's 2 additional electrons making that double bond. And these 2 electrons are free to move because there is space for it to move. So what happens is that it can actually move throughout the whole molecule like this. And just those extra 2 pi electrons can do that. And it winds up stabilizing the entire molecule. So it depends on the specific molecule, how many different locations it can be in. But the key thing really is that the electrons in that double bond become delocalized, which means that they are not stuck in one specific bond location. They are free to move between multiple bond locations. And at any given moment, it could be in any of the spots. Okay, so let's talk about how you're going to draw these. So I'm going to go back to that same example. I have CO3 2 minus. You're going to draw a Lewis structure just like you normally would. Carbon has 4 valence electrons. Oxygen has 6, and there's 3 of them, so that's 18. And there's 2 additional electrons because of the -2 charge. So that's 24 valence electrons total. Carbon is less electronegative, so it goes in the center. And I'm going to put the 3 oxygens around the outside. Each bond has 2 electrons right now, so I used up 6 of my valence electrons. Now I'm going to fill in the octets of the outer atoms first. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I used up all 18 electrons. There is a problem with this structure though, because the oxygens have full octets, but the carbon does not. And carbon must have a full octet. So you have to change one of the lone pairs into a double bond to give carbon a full 8 electrons, and each of the oxygens has a full 8 electrons now too. Now, it is a charge as an ion, so we typically would draw the brackets with the charge on the outside. So why did I pick that top one, that top oxygen, to change a lone pair into a double bond? I just did it at random. I could have very easily taken the oxygens. Oops. Remember that you can use X's for lone pairs instead of dots if you prefer. But instead of grabbing the lone pair from the top oxygen, you could have just as easily grabbed it from this left one. I could have also, if I start back here, instead of grabbing from the top or the left, I could have easily grabbed the lone pair from the right oxygen and changed that one into a double bond. Because all of those oxygens are equal, they're the same atom, they're all around that central carbon. All 3 locations are equally possible. So when we are drawing the Lewis structure for something where there's multiple locations where that double bond could form, you have to draw all of those different structures. So I'm going to go ahead and put my brackets around like this. And we use a double-headed arrow, not two arrows, a double-headed arrow to show that it's resonating. Okay. Occasionally, you will see people draw with dotted lines. So you'll see like the 3 single bonds, and then you'll see like a dotted line like this, because in reality, remember those extra 2 electrons, pi electrons in the double bond, are free to move around the entire structure there. And you would still have brackets. Occasionally you'll see it with the dotted line like that, although that doesn't necessarily show the whole picture either. Both models have pros and cons. The top one shows you that the electrons can move kind of between those 3 specific locations. The bottom, this model down here, shows you like the average. And since we can't predict where it will be at any given moment in time, the average is a little bit more like what we're going to be measuring. And this brings up an interesting point about bond length and bond order. So there are 4 total bonds in this. There are 3 single bonds and 1 double bond. So there are 4 bonds. But there are 3 locations for those bonds. So that means our bond order is 1.33. It's the bond order. Because each one of these bonds is going to behave effectively like a 1 1/3 bond instead of like a single bond or a double bond. So it's going to have strength that's in between single and double. It's going to have a length that's in between single and double because of that bond order. So anytime you're doing these hybrid structures, you count the total number of bonds and divide it by the number of locations for those bonds. So you might only have 2 hybrid structures, or 2 Lewis structures that represent the resonance, so you would divide by 2. You might have 4 different resonance structures, so you would divide by 4 for the locations instead. Let's talk about benzene. So benzene is a really interesting molecule. It has 6 carbons arranged in a hexagon like this, and it has 6 hydrogens, 1 on each carbon. So to make sure that the carbons have full octets, you're going to see double bonds. So they have this like alternating double bond. But because they're in this ring structure and there are different locations where those pi bonds can go, you wind up with 2 resonance structures possible, effectively, for benzene, where you have your hydrogens, 1 on each carbon, where instead of starting in this bottom right location, I could start in the bottom left and alternate the double bonds like this. So these would be the 2 traditional Lewis structures showing resonance of benzene. We wind up drawing very frequently the hybrid, which is showing the average between those 2, and we usually draw it using a circle, because you have the electrons in all of those double bonds are free to move about the entire molecule. And so this would be benzene. Now, if I'm using organic, like skeleton notation, it winds up being just a hexagon, because at every corner there is a carbon atom. We don't show hydrogens. And you see like just a circle like this to represent benzene. So these 2 drawings are equivalent. Make sure you can recognize that, because that pops up very frequently. And what's super special here is that effectively there are 6 electrons that are delocalized for benzene, delocalized. And so because you have 6 electrons moving throughout that ring, it makes benzene way more stable than you would typically expect a compound of its size and like atomic composition. So benzene winds up being a very, very stable compound that doesn't react like we would expect it to react. Please make sure you're able to give examples of some of the physical and chemical evidence for why benzene has these resonance structures. One of those would be bond length, which we talked about a little bit before. But because they have, I'm going to draw just the skeletal structure here. Because it's actually intermediate bonds, right? It's an average between those two structures. The bonds are somewhere between a single bond and a double bond in terms of length. Like we said, there are 6 single bonds and 3 double bonds, so that's 9 total bonds in 6 locations. So the bond order is 1 1/3 for benzene. And so because of that, the length of those bonds is somewhere between a single bond, which would be a bond order of 1, and a double bond, which would be a bond order of 2. And all of the bond lengths, all 6 bonds are equal. If I had just an alternating double bond like this, then you would have longer sides, and you'd have shorter sides, because double bonds are shorter and stronger than single bonds. So for benzene, all of the bond lengths are equal. All of the bond strengths are also equal. Okay. So let me add in strength here, bond length and strength, because of that bond order difference. In terms of chemical evidence, you're going to see that benzene does not like to do addition reactions. Addition reactions are when you would take the double bond, break the double bond, and add new elements on both of the carbons. But because benzene is so stable, because of the delocalization, like the electrons can move around, it is extremely difficult for it to break those double bonds to add something to the benzene. It's more likely that benzene would do something called electrophilic substitution. We'll do substitution reactions instead. And specifically electrophilic substitutions, because benzene has all of these extra electrons, these 6 pi electrons in those 3 double bonds are able to attract electrophiles and substitute out a hydrogen. So you have your hydrogen on your benzene. You could replace that hydrogen with a different element, like a halogen. So that is a much more likely scenario where you retain the delocalization. One final example that you might see on a question is about isomers of benzene. If you had the actual alternating double bonds and you have like 2 halogens added, the 2 halogens could be next to each other with a double bond in between, or they could be next to each other with a single bond in between. And that would be 2 different isomers. Whereas in reality, it doesn't matter, because benzene has that delocalization. When you have the 2 halogens directly next to each other, they wind up being the same compound. They do not behave like different isomers. So you'll see that there are only, when you have a dihalogen, there are only 3 distinct isomers, where they are next to each other, where they are one away from each other, and then when they are opposite from each other. But if you had the alternating double bonds, you would see a lot more isomers, because it depends on whether they're going to be like with the double bonds in between, like directly in between them, or single bonds directly in between them. It's going to increase the number of isomers there. Okay, so let's go ahead and practice drawing this. We're going to draw NO3- first. So I'm going to use my Lewis structure process. Nitrogen has 5 valence electrons, oxygen has 6, and there's 3 of them. And then I have 1 additional electron for that negative charge. So that's 24 total electrons. Nitrogen goes in the center because it's the least electronegative. Oxygens go around the outside. So I just used up 6 electrons to make those 3 bonds. And then I need to fill in the octets of the outermost atoms first. But nitrogen cannot have a partial octet. Right now it only has 6 electrons around it. It needs 8. So I need to make one of the lone pairs into a double bond. Now, because there are different locations for that, I need to draw all of the possible resonance structures. So I would draw the oxygens like this. There's one of them. And then my last one has the double bond in the other corner. So those are my 3 resonance structures for the nitrate ion. And then if you wanted to draw this with the hydrogen, you could show it interacting, if you wanted, well, you could show it interacting with the hydrogen like this, with a positive and negative ion. That's one way to do it. You could also show with the hybrid resonance structure if you choose. And with the hydrogen interacting this way. So to make it that acid, it's just going to interact with the negatively charged ion through that ionic attraction there. Okay, so here's another example question about benzene. Explain its energetic stability. So because it has 3 double bonds or 6 pi electrons, and those 6 electrons are delocalized, they're free to move around the entire molecule. It really stabilizes the ring, which makes it very difficult for the molecule to undergo any specific reactions or changes because of how stable it is. Okay, so this links to oxygen and ozone. Oxygen is O2 and has a structure like this, whereas ozone is O3, and ozone has 2 resonance structures like this. Ozone might be one of those ones that you just kind of remember the resonance structures for them because it pops up so frequently. So in O2, it definitely has a bond order of 2, double bond order is 2. Whereas in ozone, there are 3 bonds in 2 locations. So my bond order is 1.5. So because of that, it's going to take an intermediate amount of energy to break the bonds in ozone, somewhere between a single bond and a double bond, compared with oxygen, which is definitely a double bond. The double bond is going to require more energy to break it apart. And so if you're using light to do that, it's going to require different wavelength because different wavelengths have different energy. And so this section just links to a lot of others because of benzene stability. So again, there are 6 pi electrons that are completely delocalized around the ring, and because of that, it makes it extremely stable and unlikely to react with other compounds. This also links to some of our reactivity sections where we're looking at electrophilic substitution. So benzene has those delocalized electrons. There are 6 electrons that are delocalized around the entire ring. That's a lot of electrons. So if you have an electrophile, something that's attracted to electrons, that electrophile can come in and substitute for one of the hydrogens on the benzene ring and take the place of that hydrogen. So the fact that it is very stable and it's unlikely to actually break the double bond and like disrupt that benzene ring, plus having the additional electrons to attract the electrophile in, gives it a much greater favorability for electrophilic substitution reactions.